Good morning. I welcome you all to this session. In last class, we were discussing, just started the discussion on continuity equation, and we derived the continuity equation in a Cartesian frame of reference. What is a continuity equation? If we recall, it is an equation relating the velocity and density field in a flow of fluid, which is deduced from the principle of conservation of mass applied to a control volume. That means continuity equation basically signifies the principle of conservation of mass. Now, if we recall the equation, you please see here that in a Cartesian frame of reference, if you recall the equation, this is the Cartesian frame that we discussed x, y, z. The equation of continuity was like this: del rho del t plus del x of rho u. U is the x component velocity, v is the y component, and w is the z component. So typically this equation was derived from the principle of conservation of mass applied to a control volume with respect to a Cartesian coordinate system, rectangular Cartesian coordinate system. This is precisely the equations where u rho is the density and u v w are the velocity components. Now, one thing we can tell from this equation, that in a flow field, if we get a description of u, v, w as a function of x, y, z and t, as a function of x, y, z and t, v is also such functions of x, y, z and t, w is also such function of x, y, z and t, and rho is also such functions. That means these dependent variables or hydrodynamic parameters. For example, three velocity components and density are expressed as a function of independent variables like the space coordinates and time. We know these are the independent variables. Then this function must satisfy this equation, otherwise the flow is impossible. Sometimes we check whether a velocity field and density field describe a physical flow or possible flow or not. If they do not satisfy this equation, means they do not satisfy the conservation of mass. That means this is an impossible situation. These sets of functions can never represent the velocity field and density field of a fluid flow, which is the most important for the use of continuity equation. You should know that. Now, you see that this continuity equation can be defined or described with respect to different coordinate systems depending upon the geometry of the flow. Now, before doing that, we can just see that this equation expressed in Cartesian coordinate system can be written in a vector form like that: del rho del t plus this term can be written as, if you recall your preliminary knowledge in vector. So this term is divergence of rho v. Rho is a scalar, v is a vector, so rho v is a vector. You know the divergence operator is a vector operator which is I del x. For a Cartesian coordinate system, this stands like that. I, j, k are the unit vector in x, y and z direction. So we can write the operator del, which is a vector operator, k, just if you brush up your preliminary knowledge in vector. So this operator being used with a dot product, that is a scalar product with this vector, where v bar, that is the velocity field, you know this is a vector. So this has got distinct three scalar components, v and w, along x, y and z directions. So if you multiply these two vectors, that is del dot rho v dot, scalar multiplication, we simply get this. So that you know del u del x plus del v del y plus del w del z. So therefore, one way of converting any equation from one coordinate system to other coordinate system is to see the equation in one coordinate system and to find out its vector form, general vector form. So if you can do that, then we can tell that this is the vector form, and we can expand this vector form in different coordinate systems so that we can get the equation in different coordinate system. So before coming to that, I should describe one thing which probably we described earlier also. If the flow is incompressible, in the last class also, if the flow is incompressible, means incompressible flow, if the flow is incompressible, rho is constant. That means density does not change in the flow field, neither with time nor with space coordinates. What does it mean that del rho del t is 0? That means in this case, del rho, in this form del rho del t is 0. Moreover, rho will come out from the differentials, and in these operations, in this vector form, rho will come out. So ultimately the equations will be divergence of the velocity vector in vector form is 0. This is the equation of continuity for incompressible flow. In case of Cartesian coordinate, the expansion of this will be del u del x plus del v del y plus del w. That means we can write this in vector form and then expand in case of a Cartesian coordinate. Del dot v will be del u del x plus del v del y plus del w del z, because v is a vector defined by like that and del is this. Or we can straightforward get it from the equation with respect to Cartesian coordinates, that this will be 0, rho will come out and be a common factor which cannot be 0. So, del u del x plus del v del y plus del w del z is 0. This is the equation of continuity for incompressible flow. What will be the continuity equation for a steady flow? For a steady flow, please tell what is the continuity equation for a steady flow. Which term will be omitted for a steady flow? Steady flow means that parameters will not change with time. So, which term of these two terms, del rho del t, will be 0? That means for a steady flow, this is the equation of continuity. That means in Cartesian coordinate, del x of rho u plus del y of rho v. This is a special case for a Cartesian coordinate system, del z of rho w. Now, one interesting fact you must remember, that this is the continuity equation for a steady flow of both compressible and incompressible. So, if we take an additional constant of incompressible flow along with this steadiness, then rho comes constant, then we get from either of the two equations divergence v is 0. Okay. So, for a steady flow, this is the continuity equation. Now, for an incompressible flow, you see the continuity equation is divergence v 0. So, therefore, from an incompressible flow continuity equation, it is very difficult to infer whether the flow is steady or unsteady, because even if the flow is unsteady but incompressible, the equation remains same. Which is the fact? What is the why? What is the fact? Because the derivative of rho with time only appears. So, whenever the flow becomes incompressible, so it automatically goes, because rho has to be constant for an incompressible flow. Even if it is unsteady, rho cannot depend on time. Other parameters will depend on time. Since the time derivative of no other parameters appear in the continuity equation, therefore it is very difficult to judge from the continuity equation of an incompressible flow whether the flow is steady or not. For example, even whenever the flow is incompressible, state comes divergence v 0, that means this 0. So, even if the flow is steady, there is no scope of any further simplification or modification of this equation, because time derivative of no variable appears in this equation. So, therefore, the continuity equation for both steady and unsteady incompressible flow is given by divergence v 0. But for a compressible flow, there is a change between steady and unsteady equations from in the form of continuity equation. This is why? Because this is the compressible unsteady flow, and this will be the this is the compressible part. That means the unsteady flow, compressible unsteady flow, a steady flow, and this is the compressible unsteady flow. So, a compressible flow, if it is unsteady, this term will be there, and if a compressible flow, if it is steady, then this term will not be there. So, therefore, we can distinguish the steady flow or unsteady flow if the flow is not incompressible from the continuity equation. But if the flow is incompressible, whether the flow is steady or unsteady, the continuity equation will always yield divergence v is 0. This part is clear? Okay. Now, next I come to the different coordinate system. Now, let us first think that this is the equation in general for a incompressible unsteady flow. This is the divergence of rho v. If the question comes, what is the cylindrical coordinate? What is the continuity equation in cylindrical coordinate system? Continuity equation in cylindrical coordinate system. Continuity equation in cylindrical coordinate system. Continuity equation. Continuity equation in cylindrical coordinate system. So, one way, for example, what is cylindrical coordinate system? Let us conceive this cylindrical coordinate system. Let this x and this y and this z. In a cylindrical coordinate system, instead of xy, we define in xy plane the point by a radial location r and azimuthal coordinate theta, and the z will be same, that is in the z direction. That is this has come from the concept of a cylinder, geometry of a cylinder, so that at any point you will be described by a radius radial vector or radial coordinates r, azimuthal theta and this z. You know these things. That means r theta z instead of x y. These are the coordinates in a cylindrical polar coordinate system or simply cylindrical coordinate system. In that case, one way of deducing it mathematically without going for any other physical complications, that simply expand this term. But before expanding this term, one has to know the mathematical expression for this del in different coordinate system. Probably you know, if you again brush up your preliminary knowledge in vector, this del in Cartesian coordinate, as I have written earlier, that represents del del y plus k del del z, where I, j, k are the unit vector along x, y and z direction. Similarly, in cylindrical coordinate system, this will be del del r plus 1 by r, probably you know this thing, j 1 upon r del del theta plus k del del z, where I, j, k are the unit vectors along r, along this theta direction j, and along the z direction remains as it is. So, if you define I, j, k, the unit vectors along the coordinate directions r, theta and z, then this is the operator. See, one knows this thing, for him it is easy to find out del dot rho v, because v in Cartesian coordinate system, if you represent Vr, let this is Vr as the radial component of velocity, and V theta, that means this direction, the azimuthal direction is the V theta, tangential component of velocity or azimuthal component of velocity, and Vz is the z component, which we are using W in case of Cartesian coordinate system. Now we are using Vz. That means the velocity field can be expressed as its components V theta plus k Vz. So one can find out now, after knowing this and these two velocity fields, rho is a scalar function, that divergence of rho v. Well, please, any question? Please. Okay. So this will be this multiplied with this, that means del Vr del r. Sorry, I am sorry. This will be multiplied with rho. So del rho Vr del r plus rho Vr by r plus 1 upon r del del theta of rho v theta plus del del j of rho v j. Simple mathematics. That means what I do, I expand this term, vector term, this second term, in a cylindrical polar coordinate or simply cylindrical coordinate system. And if I do so, then I can write the continuity equation, another additional term, that means del rho del t plus, again I repeat the same thing, del del r of rho Vr plus rho Vr by r plus 1 by r del del theta rho v theta plus del del z rho vz. That means what I do, del rho del t, the equation, plus divergence of rho v0. This is the general vector form. That means I have expanded this in, this is the thing, in cylindrical coordinate system. That means therefore I can tell precisely this is the continuity equation in cylindrical coordinate system, where Vr, V theta, Vz are the respective velocity components corresponding to that coordinate system. So this is one way of deducing the continuity equation in different coordinate system. We can do it for spherical coordinate system also. That I left as an exercise to you. By expanding this term, this is a purely mathematical exercise. But one can again find out this from physical concept or from fundamentals. What I told in the last class is that if we have to derive the continuity equation from the fundamentals, means application of conservation equation to a control volume, then the first step is that you will have to take the control volume appropriate to a coordinate system. Now look to this figure. Now if we want to derive the continuity equation in a cylindrical polar coordinate system, which is defined by a radial location r, azimuthal, this is the azimuthal theta and z, then we will have to consider a volume which is parallel, which is a parallelepiped in case of a Cartesian coordinate system. Now the control volume will be like this, where the different planes of the control volume will be parallel to the coordinate planes. So how we will choose it? This one direction will be r d theta if this is r and this radius vector is at a angle d theta. So this angle is d theta. So another length will be dr and this will be definitely dz. That means a control volume of dimensions dr d theta r d theta dz, this type of a fluid element or a slice of a fluid element have to be considered. Now let us give some name, otherwise it is difficult to A, B, C, D and this one is E, F, G, H. Now A, B, C, D, E, F, G, H represents the control volume. Now you see we have to represent the mass flux in different directions. So there is velocity in art directions, so therefore there is a mass influx. Now let us consider due to the art direction velocity Vr, so velocities are in art direction, theta direction V theta, this is the V theta, theta direction, this is the Vr in art direction and this is as usual Vz, here we represent as Vz not as W, the z direction velocity. Now if we concentrate in the similar fashion the mass flux in the radial direction which is across the surface ABCD, this is this R surface, that means this is the surface which is perpendicular to the radial direction. So mass influx if we consider as m dot r and the mass efflux from this r plane, that means this plane EFGH, there are two r planes, that means planes perpendicular to radial direction, one is ABCD, another is EFGH. So because of the existence of the velocity vector Vr in its usual positive direction, mass will come into the control volume across ABCD surface and mass will leave the control volume across EFGH surface. So this will be m dot r plus ddr of m dot r dr, because this mass flux has changed by this amount because of a change in dr. Similar fashion we write what is the expression of m dot r, that is the mass flux across this surface, it is the volume flux times the area. So volume flux will be density, density will come for the mass, okay, let us write the volume flux will be the velocity times the area. What is the area of this surface? R d theta and dz. That means, oh already I gave this dz, again it is a duplication, okay, doesn't matter. R d theta dz and rho is multiplied to give m dot r. So therefore what is this m dot r dr, m dot r dr? That means let us write only dr m dot r dr. This will be equal to ddr of rho Vr r. So dr d theta dz I take out. Now you see the net mass efflux because of the mass flux across the r surfaces or r planes, that means the planes perpendicular to r, that means because of these two planes A, B, C, D and E, F, G, H is this minus this. So net mass efflux, I am not writing, I just tell you net mass efflux from the control volume because of the mass fluxes across the r planes, that is planes perpendicular to r direction, that means this two plane A, B, C, D, E, F, G, H is equal to this minus this, that means m ddr of m dot dr, that means this quantity. This is the net mass efflux because of the flux across the r planes. This we can write by taking 1 by r multiplied and then we r little rearrangement d theta dr dz. What is r d theta dr dz? Volume, very good. So 1 by r ddr of rho Vr r into dv. In the similar way we can find out for mass fluxes across the, we can find out the mass fluxes across the theta, that means m dot theta, that means theta direction, that means the mass flux due to the planes perpendicular to theta direction. That means now we are interested for mass flux across the planes BFGH and AEHD, two parallel planes, theta planes perpendicular to theta direction. Now because of the existence of the v theta component of velocity in its usual positive direction, the mass flux will enter the control volume across BFGA. See, let us define this, that m dot theta. And because of the same reason, the mass flux will go out of the control volume across the plane or phase AEHD, which we should write m dot theta. Why? Because this is changed at this location because of a change in r d theta. So you can write in terms of d theta, d d theta, because in the theta direction, angular direction, we are doing it, m dot theta d theta. So what is m dot theta? Please tell me. M dot theta now will be mass into the volume flow, that is v theta times the dr into dz. Very good, dr into dz. All right. Now what will be this? M dot d d theta of m dot theta d theta. This will be equal to del del theta is rho v theta dr dz. Okay? D theta, I am sorry. So this can be written as 1 by r del del theta of rho v theta into 1 by r d theta dr dz. That means this is dv, where dv is the volume of this, elemental volume of this control volume. And again, this is the quantity which represents the net mass efflux from the control volume due to the mass fluxes across these two planes, that is theta planes, BFGC and AEHD. So this represents simply the net mass flux from the mass efflux from the control volume due to the mass flux across these two parallel planes, that is the planes perpendicular to theta direction. Similar way, if we see or if we investigate the mass fluxes through planes perpendicular to z direction, what are the planes? A, B, F, E and D, C, G, H, that means bottom and top plane in this drawing. So due to the existence of the positive direction velocity Vz in the usual positive direction of the coordinate axis, the mass will come into the control volume across the phase ABFE, and similarly the mass will leave the control volume across the phase DCGH. And simply we can write now rho, this will be Vz times r d theta dr, r d theta dr. And simply this will be m dot z plus d dz of m dot z dz as usual. That means it is a change in the mass flow because of a vertical displacement dz. So d dz of m dot z dz can be written as, rather I can write d dz, that is del del z. I am writing in the fashion, though I am writing dd, but ultimately this is a partial differential. That's why I am changing from d to del, doesn't matter. So this will be, equal to del del z. You can write all these in terms of del, because in the conception there is no problem, but in mathematical notation this is not a total differential concept, because these are all partial differential, because all the quantities vary with both r, theta, z and time also. So this is an instantaneous picture, so that, and when we make differentiation with z, it should be del only. However, for the conception there is no problem. So del del z of what we can do, rho Vz and r d theta dr dz will automatically make dv. And this is nothing but the amount which corresponds to the net efflux from the control volume due to the fluxes across the jet planes. That means across two planes, AB, FE and DC, GH. So therefore we get, this is the net efflux, okay, from the control volume due to the mass fluxes across R planes. Similarly, this is the net efflux from the control volume due to mass fluxes across theta planes, and this is the mass efflux from the control volume due to mass fluxes across jet planes. So net mass efflux from the control volume, net mass efflux from control volume will be sum of this. That means del del r, if you want to have a look, 1 upon r del del r rho Vr. So I now write with this 1 by r del del r rho Vr into r. You can have a look. plus dv we will take common plus this one 1 by r del theta of rho v theta plus del z of rho vz into dv plus, if you recall, this is the net mass efflux. So continuity equation will be what? Continuity equation therefore, if you recall the continuity equation in its statement form, that the net rate of mass efflux from the control volume plus the rate of change of mass within the control volume. So control volume is dV, okay, and rho is its density. So this is the instantaneous mass within the control volume. So rate of change of mass within the control volume will be del T of rho dV plus this quantity, sorry. So plus this quantity, that means I am not writing it again, dV is equal to 0, that means this quantity. So dV will come out of this del T because control volume by definition dV is fixed. So therefore we can write del T plus this in bracket, that means this term, the entire thing dV is equal to 0. dV cannot be 0, it is valid for any volume, any finite volume of the control volume, so this part will be 0. So therefore in this similar fashion we can write that finally del rho del T plus, now I write 1 by r del r of rho Vr into r plus this, probably you can see that this I am writing 1 by r del theta, 1 by r del theta of rho v theta plus del z of rho vz is equal to 0. So this is the precisely the continuity equation. We can write it in a different form, del rho del T, if we just expand this, the differentiation VRR. So what we can get, we can write del R of rho VR plus rho VR by R. By taking rho VR as the first function, R is the second function, if you differentiate it, the school level thing, del theta rho v theta plus. So this is the equation we also derived straight from expanding the vector form of the continuity equation. So there is no need always of deriving it from the fundamentals. Just for your conception I show you, because earlier what we did, we know this vector form of the continuity equation, we simply expand this with the idea or with the knowledge that the del operator is defined in a cylindrical coordinate system like this, so that we can straightaway express this in different coordinate system. For example, the expression in Cartesian coordinate system will be del x of rho u plus del y of rho v plus del z of rho w. Similarly, for a Cartesian cylindrical coordinate system, this will be the expression. But this can also be derived again from fundamentals, that means taking a control volume appropriate to a coordinate system, for example a cylindrical coordinate system, and applying the law of conservation of mass, considering all the mass fluxes coming in and coming out from the control volume across different planes or faces, so that I can or we can derive the continuity equation. Similarly, the continuity equation can be derived in a spherical polar coordinate system, which again will make more complications, because the control volume will be little complicated by geometry, either by using the fundamental concept or by expanding this form, which is left as an exercise to you. Now after this I will go to a very important concept in a fluid flow, which is the concept of stream function. What is a stream function? Concept of stream function. Now we know that for an incompressible steady flow, or we should not always tell that is incompressible steady, even for an incompressible flow, that means even if it is steady or unsteady, the continuity equation is such. That means if one tells that I have an incompressible flow, my velocity fields are given as a function of space coordinates and t, with scalar components u as a function of x, y, z, t, v as a function of if it is a Cartesian coordinate system, or if it is a coordinate cylindrical coordinate, it will be a function of r, theta, z. So I am just describing in general. If one tells and claims that his flow is incompressible, one can tell him, okay, please wait, I will check whether your velocity functions explicitly given in this form satisfies this particular equation or not, divergence of V is 0. If it satisfied, we will tell, okay, your flow field is possible. If it doesn't satisfy, then we can tell it is an erroneous flow field. This velocity function can never define a incompressible flow field. This is the concept. So therefore, if we come again to mathematics, the divergence of the velocity vector is 0 for an incompressible flow. Let us consider a Cartesian system. First, simply, so it is nothing but del u del x plus del v del y is 0. And always we consider a two-dimensional flow. Stream concept of stream function is associated only for a two-dimensional flow. You must know this is not for a three-dimensional flow. In three-dimensional axisymmetric flow only, which again reduces the three-dimensional flow in a two-dimensional flow, I will explain it afterwards, then we can define the stream function. But usually the stream function is defined only for two-dimensional flow. So for a two-dimensional flow, the expansion of this term for a Cartesian coordinate system is like that. Or in other words, in a two-dimensional flow, defining u and v as a function of x, y and t, the continuity equation for an incompressible flow at any instant is this. Okay. Now if I define a function psi, which is a function of x, y and t at any instant t. If it is a unsteady flow, the variable t will come, otherwise it will be a function of x and y only. That means if in a two-dimensional flow field I defined a function, think mathematically first, I defined a function so that this function satisfies this condition, u is equal to del psi del y and v is equal to minus del psi del x. That means this function is such whose partial derivative with respect to y defines the x component of velocity at a particular point. If it is a function of time, this will be a function of time also. Similarly, its derivative with respect to x with a negative sign defines the velocity, y component velocity at that instant. Then this function is defined as the stream function. Now question comes, why so arbitrarily we are defining a function such that u becomes del psi del y and v becomes del psi del x? Mathematically it is understandable. Okay, we define a function psi which is a function of x, y and t in such a way that u and v are defined in terms of this function in this manner, then this function is called the stream function. But what is the significance of it? What is the significance of it? Let us now see the mathematical significance. If you define this way, then if we put this stream function in continuity equation, that means if the continuity equation is now substituted in terms of this stream function, what we will get? First term del square psi del x del y. What we will get in the next term? It is minus del square psi del y del x. Now if psi is a continuous function of x and y, you know that this order change doesn't have any difference. That means del square psi del x del y is del square psi del y del x. That means if you differentiate psi first with x and then with y, or first with y and then with x, they will be equal if the function is continuous. Again brushing off your school level mathematics. So therefore this becomes is equal to 0. That means it is automatically satisfied. That means we don't get any extra equation as a continuity equation if the flow field is defined in terms of stream function. Try to understand, this is a real tough concept at this level. Only by reading books you may not understand this. That means instead of defining the flow field in terms of uv, if we define a flow field in terms of stream function, it automatically satisfies the continuity equation. Because if we substitute this stream function, because stream function is defined this way, so that if we substitute this, continuity equation gets 0. That means if we define the flow field in terms of a stream function, so continuity equation is automatically satisfied. That means we do not have an extra equation to satisfy the conservation of mass. That means the equation is automatically satisfied. This is the mathematical implication of stream function. Let us see the physical implication of stream function. Now before recognizing the physical implication of stream function, let us consider one thing, that stream function is a function describing psi as a function of xy. Now a change in stream function, one interesting thing now we like to inspect. Now we write a total change in stream function xyt. It can be written in mathematical form del psi del x, okay, del psi del t dt plus del psi del x, this you know, dx plus del psi del y dy in a two-dimensional. Now at any instant, if we are interested at any instant value or for a steady flow, this term is not coming into picture. So therefore d psi is equal to, that means the change in the stream function at any instant, or in a simplified manner we can think of a steady flow where the change in the stream function can be defined like that. This is very simple. It is no way connected to fluid mechanics concept, that if there is a function of xy, the change in the function psi d psi is the change due to x and change due to y, del psi del x dx plus del psi del y dy. Now what is the definition of stream function? This function is not a very arbitrary function. This is such a function that u is equal to del psi del y, or simply del psi del y is equal to u, and v is equal to minus del psi del x. So therefore here I can write minus v dx plus u dy. What is the value? Can you tell me along a streamline? Along a streamline, what is the value of the right hand side? For a streamline, the equation of a streamline we know. What is the equation of a streamline? If you recollect, it is dy dx is v by u, because the tangent at that line at any point is the direction of the velocity vector. For a two-dimensional case, streamline is dy dx v by u. So therefore, v dx minus u dy or u dx minus v or u dy minus v dx is 0 along a streamline. So therefore, along a streamline, if this is a streamline, this value is 0, which means d psi is equal to 0 along a streamline. That means the psi function along a streamline, let us consider this is the x, this is the y, this is the z, and this is a streamline. So sorry, z concept doesn't come, it is only xy concept. I am sorry, let it is like this. There is a x and y, and this is a streamline. So psi functions, this is a streamline, this is a streamline. So what we get? Along a streamline, the values of psi are same. That means psi is equal to constant along a streamline. So this is proved. So this is one of the very important conclusions, that along a streamline d psi is 0. That means psi is equal to constant. So psi is equal to constant along a streamline. So therefore, in a two-dimensional flow field, we can define streamlines by telling different values of psi, psi 1, psi 2, psi 3, psi 4, which are the constant value. Because psi is constant along a streamline, it doesn't change along a streamline. So a streamline can be specified by giving a constant value of psi, stream function. From this, we can proceed another step further regarding the streamline, physical implication of streamlines. Let us consider again xy, the two dimension, and let us consider two, okay, psi 1 and psi 2, the two streamlines, psi 1 and psi 2. Let us consider one point A on a streamline, another any point A and B on two streamlines. Let us join. Okay, now let us consider a control volume. Let us consider a control volume whose dimension in this direction perpendicular to this plane of the figure or plane of the paper is unit. Let 1 unity, and this length let ds, that is the length joining 2 points on two streamlines defined by stream function psi and psi 2. Let therefore this length, this is dy and this is dx, obviously. Now let us consider the flow field is such that because of which there is a flow coming into this control volume across this surface of length ds and unit dimension, plane unit dimension in this direction. If there is a flow coming into the control volume, and if we consider the flow going out from these two planes, then what is the flow coming out from this? It is u dy, volume flow. Now I have told that this concept of stream function we are discussing for an incompressible 2D flow. This is always valid, incompressible 2D flow, because from the very beginning we have defined that the continuity equation which is getting satisfied is del u del x plus del v del y is 0. That means basically it is two dimensional and incompressible. So in case of incompressible flow, the volume flow rate instead of mass flow rate we can use, because rho becomes a constant scale factor. That means the volume flow which is coming to the control volume across these planes must go out from these two planes. If we consider through these two planes, the volume, the fluid is going out. So this is the volume flow rate across this phase, and this is the volume flow rate across this phase, because the area of this phase is dy into unit distance and area of this phase is dx into this distance unit. So therefore we can write the dq, if I tell the dq amount of flow, volume flow, q is the usual nomenclature for volume flow rate, is crossing these planes joining A and B, must be equal to u dy. Now this vdx in this frame of reference where y is positive in this way, that this will be minus vdx, because v is always negative sign. So minus vdx plus of minus vdx, that means u dy minus vdx. Now what is u dy minus vdx? This is the difference d psi between the 2 points, because if I relate psi 1, psi 2 minus psi 1 as d psi, it will be del psi del x as we have seen dx plus del psi del y dy. That means u minus v dx plus u dy. That means this quantity d is equal to d psi. That means this gives the difference of stream function between these two streamlines. So this is the flow rate per unit length in the perpendicular direction. So this gives the most important physical conclusion, that the difference in stream function between two adjacent streamlines, between two any streamlines, gives the volume flow rate across these streamlines. We understand volume flow rate, within these streamlines per unit width in the normal direction. There is no volume flow rate across a streamline. That means if we consider a control volume like that, the volume is flowing like this. So this is the one. So if we consider two streamlines, and this consists of a stream tube, that means bounded by two streamlines, then we can tell the volume flow through these channels made by two streamlines is given by the difference of the stream functions defining these two streamlines per unit length or per unit width in the normal direction. Because if you see the unit, you see that psi 2 minus psi 1 u dy minus v ds, this unit is meter square per second. That means this is the volume flow rate per unit width in this direction. So it is clear. So therefore we can tell that the stream function signifies this physical role, that difference between this stream function gives the flow rate within the two streamlines. Well, I think we can conclude here. So streamlines is like, stream function is constant along a streamline. Stream function is a function of x, y such a way that its derivative with respect to x and y coordinate defines the velocity component in such a way that it automatically satisfies the equation of continuity in an incompressible two-dimensional flow. This is number one. Number two is the stream function remains constant along a streamline. And number three is the difference between the stream functions between two streamlines gives the rate of flow through these two streamlines along the channel formed by two streamlines per unit width or length in the perpendicular direction. Thank you.